So welcome to the afternoon session on relaxers. My name is Henry Krakauer from the College of William and Mary, and I've been asked to chair this session. So the first speaker is Takeshi Egami from University of Tennessee in Knoxville and Oak Ridge National Laboratory.
Good afternoon. I'm happy to be back to this conference and thanks for the invitation. So I've been focusing on liquids and gases in the last 10-15 years or so, and relaxer as a part of this glassy behavior. So I'd like to discuss relaxer phenomena in a larger context of liquid and glass behavior. And this subject is interesting because there's a really deep unsolved problem. Once Phil Anderson declared the deepest and most interesting unsolved problem in solid-state theory is probably the theory of the nature of glass and glass condition. And the reason why this is difficult is that liquid and glass do not have periodicity, whereas most of the condensed matter theory is based upon periodicity of layers, plane wave approximation, etc. And not only this, but the liquid is inherently dynamic. There's no structure in a sense. There's no elastic scattering from liquid. So I call this kind of a group of systems not just a soft matter. Soft matter is misleading because being soft is not important, right? What's important is that it is dynamic and it's aperiodic. So I call them DAM, dynamic aperiodic matter. So I'd like to discuss relaxer in the context of DAM. And the reason why DAM is difficult is, again, it's dynamic, and there's no lattice, so everything is strongly correlated. So you have to face many body problem right on, head on, and that's why this is difficult. But at the same time, that's why it is important. It's a really a sort of 21st century physics subject. One of the major questions in this DAM is the liquid, how the liquid will become glass. So the property of liquid is characterized by this viscosity, or in terms of time scale, if you divide viscosity by shear modulus, you get sort of Maxwell relaxation time. And this is about a picosecond or so in regular water. And the glass condition is defined by viscosity becomes 10 to 34, so that means relaxation time becomes a minute or more. So essentially that the time scale changes from the liquid to glass by 15 orders of magnitude. 15 orders of magnitude. It's a cosmological number. And yet the structure of liquid and glass are not that much different. So why you get such a big difference in viscosity or time scale in spite of similar structure has been a long-standing question. So this kind of glassy behavior is seen in many materials. Glassy behavior means relaxation behavior, frequency dependence, and freezing out of the equilibrium to non-ergodic state. And because of that, usually the behavior depends on thermal history. So that's a glassy behavior, and seen in regular liquids and glass we call structural glass, but it doesn't have to be structure. Strain glass and relaxer, strain glass, and human society, particularly around Washington, D.C. So it's all over the place, and maybe by studying liquids and glass we can learn about ourselves and our society. In the future, I'd like to write a book about how physics can understand society and politics particularly. And the example of relaxation behavior is, as you know, that permittivity goes out of equilibrium below freezing. Therefore, that the permittivity depends on, or polarization depends on freezing in a field or freezing in zero field. And this is exactly seen in spin glass, the same thing. If you feel cool in magnetic field, you get one thing, and zero field is like that. And then the departure point defines this freezing point, the freezing temperature. And the phase diagrams are similar also in spin glass and relaxers. And then this is the frequency dependence of this, in this case is the relaxer, and in this case is the spin glass. So everything behaving really essentially the same way. So phenomena are very similar. And that's the dependence of the remnants on frequency. And then you can see that, frequency, this is for the relaxer. The frequency from 10 to 12 to essentially static changes, only this much. So there's a huge 15 orders of magnitude or more change of time scale in this glassy behavior. In real glass, in real liquid, or in this relaxer, either case. And as you can see that this polarization disappears, this case is PMN, at about 600 Kelvin. So all this happens in the temperature range below this temperature. And today I'd like to focus on the origin or meaning of this temperature called Burns temperature. Essentially the idea is that that's where everything starts. Everything, the glassy behavior starts. And then once starts, it slows down. So freezing or glass transition is just a consequence. We have to understand this behavior. And the study of this dam is difficult because, as I said, everything is dynamic. So the elastic scattering intensity, strictly speaking, is zero. Everything is quasi-elastic. So we have to study not just SQ, but SQE, energy-dependent scattering intensity. And what we call structure function is simply an energy-integrated inelastic scattering intensity. For instance, if you do X-ray scattering, the usual resolution of X-ray scattering is like EV. So that integrates, that's much bigger than the energy scale of, say, phonon or this vibronic degrees of freedom. Therefore, in X-ray scattering, you are essentially energy integrating. And as a result, if you do that, you get time dependence left out. Essentially, you get a snapshot, or what you call, the same time correlation function. So what we usually refer as a structure in this kind of disordered system is this snapshot structure. But the real structure depends on time. So we have to understand this time dependence to understand dynamics. But everybody try to just predict the behavior based upon the snapshot. And that is like buying a stock knowing only today's price. Nobody does that. Right? You always study the time dependence. But somehow that there's some fixation that you start with this snapshot and then try to predict everything. So I'm going to show you it doesn't work. And the reason why only the snapshot has been studied is because inelastic measurement is slow and difficult. So we used to use reactor, for instance, in inelastic X-ray, the neutron scattering measurement. And you fix Q, for instance, and then change energy. And usually this kind of scan takes hours. So even just one scan takes, hours. So the experiment is easy. In the morning, you set up several runs and go to mountain or something and have a nice dinner and come back, and then the results are ready. So by that, it's impossible to get enough SQE information. That's why only the snapshot has been studied, and no realistic study of inelastic measurement has been done. But today, because of the advance in the technology instrumentation, for instance, by using pulsed neutron system, we can get scattering as a function of momentum and energy in big space like that at once. So what used to take a month now takes only 4 hours. So typically we do our experiment in 4 or 5 hours scale. So it's much easier. And therefore, we now can study not only this SQE, that's what you measure, okay? That's what you measure. But if you have enough data, not just one Q, but many Qs and many E's, therefore you need a two-dimensional data of SQE. And that's what Mr. Pulse system gives you, okay? So if you have that, we can transform from Q, momentum space, to the real space, and to get the dynamic PDF. I will show you some case of a dynamic PDF. And even further, from energy to time into Van Hoff function, so-called Van Hoff function, time-independent PDF, Pedersen function. That's the snapshot gives you this, PDF. That's again instantaneous, so same time correlation function. Now, by this technique, we can get time-dependent PDF so that we can see how PDF will decay with time. Now, Van Hoff function was defined long time ago. His paper is 1954, right? Long time ago. But nobody tried because, in order to get this down here, you really need a very good data of SQE over a wide range of Q and E, and it has not been possible for a long time. But now it's possible, so we can get it. So I will show you an example of Van Hoff function. Today we just discussed dynamic PDF, but in our group, we are getting Van Hoff function all the time. So this is an example of Van Hoff function. This is done by inelastic X-ray scattering. Usual X-ray scattering has a resolution, as I said, EV or something. But with this big advanced technique and using backscattering, the resolution now is better than 2 millivolt, 1.6 millivolt. So with this kind of amazing resolution, and in this system, this is the Spring 8 spectrometer in Japan, and they have 24 detectors, so we can get a lot of data. So we can get this kind of two-dimensional SQE in about 12 hours. It used to take forever, but now we can do it in 12 hours. And the inelastic X-ray scattering on this is for water. Water was done before, but only at the low Q to look at phonons. And here, actually, you see phonon, but it's so weak. Actually, somehow, again, people have fixation to the phonons, and they study phonon with a difficulty. But the spectral weight of phonon is less than 5%. 95% is this kind of quasi-elastic scattering. And nobody went beyond about 1.5 inverse angstrom to study this behavior, because it's, first of all, it's hard to see. And this is the quasi-elastic, and there's some Q dependence, but it's hard to make anything out of this. It looks like fish or squid, but beyond that, you can't say much. But if you Fourier transform, then you get this. That's the Van Hoff function. So the cut at the 0, time 0, is this snapshot. Okay, that's a regular PDF. So that's itself, and that's the first neighbor, second neighbor, and etc. Okay, third neighbor. So this cut was that something we used to do, we used to see. But here it tells you how it evolves with time. So as you can see that it decays with time, and then this is not straight line, it's going to the right and this is going to the left, and they're going to merge. So anyway, I don't have time to get into details, but we can study the correlated molecular motion from this pattern. We are now studying how the salt could affect this and etc., or organic molecule will affect, etc. Essentially, we are studying wine, for instance. So from the way that first peak decays, this is the way it decays with time, and from this we can find out how the bond gets reorganized. We can determine the bond lifetime out of this measure, and we were able to make direct connection between this bond lifetime and viscosity. So we now understand the origin of viscosity, not only in water but in liquid in general. So today I focus on dynamic PDF, which is the in this dynamic structure factor change from Q space to R space. Actually, we use this dynamic PDF for superfluid helium and got a remarkable result, but I don't have time to get into that. So this is the dynamic PDF of PNN as a function of energy. This is about it's about Curie temperature below the Brownian temperature, and again, in this case, zero energy corresponds to not the instantaneous, but average, time average. So average structure of this is cubic. So if you analyze this energy equals zero structure, you get cubic symmetry. And if you integrate everything, then you get the snapshot. Okay? Then you can see that energy dependence is not simple. For instance, this guy shows up only above this temperature, this one, energy, and this one. And that's the hallmark or signature of dynamic polarization. And low energy static structure shows polarization only at, that's the signature again of dipolar moment, distortion of lead environment. And this disappears at room temperature, okay? So that means low frequency or radio frequency response. This is neutron scattering, so we are talking about dynamic. When I say dynamic, it's picosecond, right? Anything below 10 pico or longer than 10 picosecond becomes static. So static one disappears at 300. But here, 10 to 12, 15 millivolts correspond to about 4 Tesla, I'm sorry, 4 terahertz, okay, 4 terahertz, quarter of picosecond. At this time scale, this polarization persists up to the Brownian temperature. So there is a picosecond level, the polarization, which persists up to Brownian temperature. And, radio frequency and below, slow one dies at room temperature, PC.